Now, adding up the terms of a geometric series is just as logical as with an arithmetic one, but it's a slightly different type of logic that we use to get the formula. You'll remember with the arithmetic sequence, if we're adding up things like, say, the numbers from 1 to 100, our strategy was to line them up and get the end of the line to come around and make pairs. And we had that formula that relied on counting the number of pairs and then multiplying that by the first and the last, because we knew that all the pairs added up to the same thing. Now, with a geometric series, it's a little bit different. Let's start by thinking about what we know is the sum of a geometric series. Well, it's the first term. We define that as A. And then the second term is A multiplied by that common ratio R. And then we multiply R by R again and again and again in each term. Now, remember that it goes up to this. And we know this because we know the formula for the nth term is AR to the n minus 1. So that last term, if we're summing all n terms, has n minus 1 up there in the index, not n. Okay, so here we're going to do a little bit of a trick. We're going to take all of the terms in this series and multiply every single term by r. Why are we doing this? Well, you'll see in a moment. So on this side, if that's the sum to n terms, then if I multiply it by r, I've just got r times the sum to n terms. And then all of the terms get bigger, don't they? Well, they get bigger if r is greater than 1. If r is greater than 1, then every term is bigger than the last, isn't it? Whereas if r is less than 1, say if r was half or something like that, then if I've multiplied everything by a half, I've actually made them smaller. So it depends whether r is greater than or less than 1. But let's just imagine it's greater than 1 for now, and that this is a series that's going up in size with each term. Now I can use a trick. We'll treat them like simultaneous equations. We'll call this one equation 1 and this one equation 2. Now what we're going to do is say, well, all right, if this equation 2 is potentially bigger, because if we're imagining that the ratio is greater than 1, so these ones are bigger numbers than those ones, then one thing that we could do is that elimination technique of taking one whole equation away from the other. So let's start with the big one and take away the small one. Now, can you see that all of the terms pretty much match up, except this one doesn't have a partner that's the same, and this one doesn't have a partner that's the same. So if we do all of these terms minus all of those, nearly everything will get taken away. And what we'll be left with is this part, a times r to the n, minus this term. So we end up with a nice, simple equation. All right, what can we do with that? Well, both terms here share something in common, so we can factorise, and same here. If I factorise this side, I can bring the sum to n terms out the front, and I end up with r minus 1 in the brackets. And here, taking a out the front of some brackets, I've got r to the n minus 1. So if I want to get the sum to n terms all by itself, I need to just divide both sides by r minus 1, and I'll get this formula here. And this is the one that you'll find on your formula sheet, where it says the sum to n terms is a times r to the n minus 1 over r minus 1, where a, of course, is the first term. We're used to that, and r is the ratio. Now, let's consider what would have happened, though, if r was less than 1, if it was a fraction, and all of the terms that we made in this equation were actually smaller than their counterparts up here. Well, then the logical thing to do when we took one away from the other would be to start with the bigger one, which would be this set of numbers, and subtract these ones. So we would have had these two terms around the other way, and we would have had these two terms around the other way. We could have then factorised them just like we did, and we'd just have these terms switched. And then when we divided by that, we'd get a formula that looks almost the same. Now, what's the point of this? Well, we've got two versions of the same formula. You can use this one for everything. It's just you'll end up with lots of negative numbers, and it gets awkward if r is less than 1. So we say when r is less than 1, use this version of the formula. It just comes out neater. And when r is greater than 1, use this version. Now you can throw anything you like into that formula. As long as you know the first term and the ratio, you can find the sum of any number of terms in a GP.